Okay, so hi everyone, and welcome to the YEA Big meetings for today. And so first we have an algebra level AMC lecture by Ethan Ham.
Today I'm going to talk about Vieta's formulas, which appear often enough on AMCs that it merits its own lecture. Can you guys see this? Can you guys see my screen? Hello? Sorry, can you hear me? Okay, yeah. Wait, Aaron, can you see my screen? Okay, great. Let's get started. So Vieta's formulas are like formulas that allow us to, what was that? Sorry. That allow us to relate the roots of a polynomial with its coefficients. So how it works is, right, let's say we have, you guys have probably seen some of this before, but if you have a degree 2 polynomial, ax squared plus bx plus c, right? This is going to have two roots, which are negative b plus or minus whatever over 2a. And as you guys probably know, so we'll call these roots R1 and R2. So as you guys have probably seen before, we know that R1 plus R2, the sum of the roots, is equal to negative b over, and the product of the roots R1, R2 is equal to c over a. So essentially what this allows us to do is it allows us to relate the roots of a polynomial, right, R1 and R2 with its coefficients. And the reason this is true is if the roots are R1 and R2, then we can factor this polynomial as a times x minus R1 times x minus R2. Since R1 and R2 are the roots and we need a here to take care of the leading coefficient to make sure that it's a. So then this expands as ax squared minus a times, when you expand this out and collect like terms, you get ax squared minus a times R1 plus R2 x plus a times R1 R2. However, we know that this polynomial and our original ax squared plus bx squared plus c polynomial are the same, right? So that means that negative a times R1 plus R2 has to equal b, and a times R1 R2 equals c. So that's how we get these two. And we can also extend this to polynomials of higher degree. Whoops. Yeah, we can also extend this to, wait, how do I clear this? Okay, yeah, we can also extend this to polynomials of higher degree. So what we can do is we can, for example, if we have ax cubed plus bx squared plus cx plus D, right? Then let's say it has roots R1, R2, and R3, which it must have by the fundamental theorem of algebra. So that means that we can factor this as A times x minus R1 times x minus R2 times x minus R3. And so when we expand this, we get what? Ax cubed minus A times R1 plus R2 plus R3 x, and then the next term, the x squared, from expanding this, because we can, for example, to make x squared, we can pick negative R1 x and x, or negative R2 x and x, or negative R3 x and x. So, and then similarly to make the x term, we can pick R1, R2 and x, R2, R3 and x, or R1, R3 and x. So we get R1, R2 plus A times R1, R2 plus R2, R3 plus R3, R1 x. And then the last term is minus A times R1 plus R1 times R2, my bad, times R3. So this means that R1 plus R2 plus R3, right? This has to equal what? Well, since negative A times R1 plus R2 plus R3 equals B, then this equals negative B over A. Since A times this equals C, then R1, R2 plus R2, R3 plus R3, R1, this equals C over A. And for this one, for this, right, negative A times R1, R2, R3 equals D. So the product of the roots is equal to negative D over A. Wait, no. Okay, so now this can be extended to general polynomials, right? This pattern. Oh, not again. So now if we have, for example, a polynomial a(n) x to the n plus a(n minus 1) x to the n minus 1 plus all the way to a1 x plus a0. Then what we can do here is, let's say the roots by the fundamental theorem of algebra are R1, R2 through Rn. Then we'll let Sk denote what? The sum, let's see. How? So Sk is going to equal what? The sum over all what? Let's see, subsets. The sum over all subsets S of 1. You know what? Let me just give a few examples. We'll define S1 equals R1, R2, sorry, plus, so S1 will be the sum of all the roots. S2 will be the sum of the product of all pairs of roots. So this will be like R1, R2 plus R1, R3 plus dot, dot, dot plus R2, R3 plus dot, dot, dot plus Rn minus 1 Rn. So S2 is the sum of all pairs of the products of all possible pairs of distinct roots. And similarly, S3 is the product of, is the sum of the product of, is the sum of the product of all possible triples. So R1, R2, R3 plus R2, R3, R4 plus dot, dot, dot. Right? So in general, and in the end, we have Sn will be this product of all of the possible n tuples. So since there's only n roots, then Sn will just be the product of the roots. And so you can do the same thing that we did before with a higher degree polynomial. We can say that this is equal to an times what? Times x minus r1 times x minus r2 all the way to times x minus rn. And so now what we can do is we can expand this polynomial and we can compare the coefficients of this polynomial with this polynomial, and they have to be equal. And that'll give us a relationship between the roots, and more specifically, these like symmetric sums of the roots. It'll give us a relationship between these and the coefficients. More specifically, if you actually do this expansion, what you'll get is that sk is equal to -1 to the k times a n minus 1 over a n. And so as a result, so what happens here is we have, what do we have? So I'm just showing how Vieda's formulas work, and then we're gonna go on to some practice problems. So for example, if we do k equals 1, then S1 is equal to the sum of the roots, right? So the sum of the roots of the polynomial equals what? Well, k is 1, so we get negative of an minus 1 over an. And so now, as a result, and this is exactly what we expected from looking at the cases where we have a quadratic and a cubic polynomial, right? The sum of the polynomials should be negative an minus 1 over an, just like how with ax squared plus bx plus c, the sum of the roots was negative b over a. So in general, this is Vieda's formula. But you, in general, on AMCs, you probably won't have to do this for more than what is it? You probably won't have to do this for more than you probably won't have to do this for polynomials of degree more than 3. So let's do some problems involving this. Vieta's formulas are pretty useful since they appear quite a bit on AMCs. So one pretty rudimentary problem is this. Let's see. Smaller. So this is an AMC problem. We have A and B, which are the roots of the equation x squared minus mx plus 2 equals 0, and a plus 1 over b and b plus 1 over a are the roots of x squared minus bx plus q. So what is q? Well, this problem is pretty basic. It's a pretty straightforward application of Vieta's formulas. So what happens here is we know that in a quadratic polynomial, q is equal to the product of the polynomial, the product of the roots of this polynomial. And we're given that this and this are the roots. So this is equal to a plus 1b times b plus 1 over a. And when we expand this, what do we get? We get ab plus 1 over AB plus, let's see, 1 over B times B is 1, and 1 over A times A is 1. So plus 1 plus 1. So now we want to find what AB is, right? But A and B are the roots of this. And by Vieta's formulas, we know that the product of A and B is 2, since A and B are the roots of this polynomial. So AB equals 2. So then plugging this in for Q, we get 2 plus 1/2 plus 1 plus 1, and we get 9/2. So that was a pretty basic example of an AMC problem involving Vieta's. And I'm going to go through a couple more differently flavored problems. Let's see. Okay, let's go over. Why is it not uploading? Sorry, the picture is not uploading. Okay, here we go. This is actually an AMY problem, but it's this one too is also a pretty straightforward application of Vieta's. So R, S, and T are the 3 roots of this equation. 8x cubed plus 1000x plus 2008 equals 0. So we want to find R plus S cubed plus S plus T cubed plus T plus R cubed. So now the critical observation for this problem is that by Vieta's formulas, right, the sum of the roots R plus S plus T is actually 0, because we know that the sum of the roots is 0 because the x squared term is 0. And the sum of the roots is negative of the ratio of the x squared term over the leading coefficient. So the sum of the roots is actually 0. So R plus S is equal to negative T. Similarly, S plus T is equal to negative R. And T plus R is equal to negative S. And we get, so this is equal, so the thing that we're trying to find is negative of R cubed plus S cubed plus T cubed. And to find this, what we can actually do is, we know that what? So we know 8R cubed plus 1001R plus 2008 equals 0. So that means 8r cubed equals negative 1001r plus 2008. Similarly, we know that 8s cubed equals negative 1001s plus 2008. Whoops, that was not a very good 8. And 8t cubed equals negative 1001t. Oh, minus 2008, my bad. It should be minus 2008. Let's erase this. Minus, not plus, because we know that for example, 8s cubed plus 1001s plus 2008 is 0. So what we can do is we can actually add all of these equations, and we get what? 8 times r cubed plus s cubed plus t cubed equals, first of all, we have negative 1001 times r plus s plus t. But earlier we found that r plus s plus t equals 0. So when we add this, and this together, they all just die because r plus s plus t is 0. So we get negative 3 times 2008. And then from here, we can divide out by 8 to find the value of this and plug it into here, and then we will get our answer. And let's see. So are there any questions about this problem? Okay, I'm gonna move on then. Our last example problem is, which one should we do? Okay, I think this one is pretty instructive, actually. So the zeros of a polynomial x squared minus ax plus 2a are integers. So let's find all of the possible values of a. So this problem involves like a variety of a couple different techniques, and it also shows us the power of like why Vieta is so useful, right? So we know that the roots are integers, and we know some stuff about the coefficients. So when we have like a relationship between the roots and the coefficients, we can try to use Vietas. So let's say the roots are m and no, those are kind of hard to write. What are x and y, right? So if x and y are the roots of this, x and y are integers, first of all. No, actually x is already there. Let's just use m and n. M and n are the roots. These are both integers. So what do we know? We know that the sum of the roots, m plus n, is equal to a, right, by Vieta's formulas, because this is negative a, so the sum of the roots, m plus n, is a, and the product of the roots, mn, equals 2a. So then we want to try to find the sum of all possible values of a, which is the sum of all possible values of m and n. However, the trick here is that if we multiply this entire equation by 2, we get 2a here, and mn equals 2a. So that means mn equals 2 times m plus n. So that means that mn, so since we know mn equals 2 times m plus n, since m plus n equals a, so 2 times m plus n is 2a, so mn equals 2a, right? Then mn minus 2m minus 2n equals 0. And then we can use Simon's favorite factoring trick and add 4 to both sides. So if we add 4 to both sides, we can see that this side factors as m minus, that was not great, m minus 2 times n minus 2 equals 4. But it turns out that m and n are integers, right? So m minus 2 and n minus 2 must be integers. So we have 1, 4. Here are the possibilities, or 2, 2, or -1, -4. These are the possibilities for m minus 2 and n minus 2. And we want to find all possible values of m plus n. We could also switch these around. So we have 4, 1 and -4, -1. But as you can see, that's obviously symmetric. So it'll give the same value for m plus n, which is a. So we don't need to do that because that's redundant. So from this case, we get m equals 3, n equals 6. So we get 9. For this case, we get, for the second case where this is 2 and this is 2, we get they're both equal to 4. So the sum of the roots m plus n, which is a, is 8. And for this case, when m minus 2 is -1 and n minus 2 is -4, we get what? We get m equals 1 and n equals -2. So that gives -1 for A. And then we add these up and we get C, 16. And yeah, I think we have time for one more problem. I might go a little over, sorry about that. But we have time for one more problem. Let's see. So this is a pretty recent AMC problem. Wait, I think this was on the last AMC 10 actually, and 12, but okay, this is kind of a long problem statement. So a quadratic polynomial with real coefficients and leading coefficient 1 is called disrespectful if the equation P of x equals 0 is satisfied by exactly 3 real numbers, and there's a unique disrespectful polynomial P squiggle of x for which the sum of the roots maximized. So what is P squiggle of 1? Yeah, so we know, so we're looking at the roots. So we can, so the idea is that we can try to use YEA's, right? R and S, P squiggle of x equals what? It equals x minus r times x minus s. So there's exactly 3 real numbers. So let's look at the equation P. You know what? We'll just consider P of x equals x because the squiggle is too annoying to write. Let's say P of x equals 0. We want to find solutions to this, right? Now, if this equals 0 and the roots of P are r and s, then P of x has to equal r or s, because when we plug P of x back into P of x, we need to get 0, and the roots of P are r and s. So that means P of x must equal r or it must equal x, so that we have P of x equals 0. So if it's satisfied by exactly 3 real numbers, then so we have P of x equals r and P of x equals s. And since so we have this or this, and since this equation is satisfied by exactly 3 real numbers, then one of these equations, right, these are both quadratic equations, so they should have 2 roots each. But since there's only 3 real roots, there's 3 unique real roots, one of these must have a double root. So let's say that this has a double root, right? So when we expand this, we get what? X squared minus r plus s x plus rs, right? This equals r when we expand p of x. This is kind of like, so it doesn't actually directly involve Vieta's formulas, but the approach is inspired by Vieta's because we see the sum of the roots and we see the roots, and as a result, we can use Vieta's to relate the coefficients of a polynomial with its roots. So we have that this holds by expanding this. So if we subtract r from both sides, then this equals 0. And we want this equation to have a double root. So that means that r plus s, so that means the discriminant is 0. So that means that r plus s squared must equal 4 times rs minus r, right? Because for it to have a double root, discriminant must be 0. So let's take a look at this equation. Okay, so the equation that we had was, I think, our equation was that r plus s squared equals 4rs minus 4r. So then if we subtract 4rs from both sides and we expand this, we get r squared. Then we have 2rs, but we subtracted 4rs. So now we have minus 2rs plus s squared. So this equals r minus s squared, which is equal to negative 4r, right? And so what happens here is now we want to solve for s in terms of r. So r minus s, well, it equals negative 4 because we subtracted 4rs from both sides of this equation. So r minus s equals plus or minus, the square root of this is 2 root negative r. So that tells us that r must be negative since r and s are both real. So s equals r plus or minus 2 root negative r. So now we want to find the polynomial p squiggle of x for which the sum of the roots, which is the sum of r and s, is maximized. So the sum of the roots r plus s is going to equal 2r plus or minus 2 root negative r. Now, since r is negative, if we had a minus, then this would be a negative number minus a positive number. So that would be negative. And that, in contrast, if, so that means that that would be too small, right? It would not be the maximum. So that means the maximum occurs when this is a plus, not a plus or minus. So we want to find the maximum possible value of this, the maximum possible real value where r is a negative. So this is, so if we consider x equals root negative r. Then x squared is equal to negative r. So r equals negative x squared. So 2 times negative x squared, since r equals negative x squared, since x squared is negative r, plus x equals, right? So that's what this is equal to. And we want to maximize this. So we can see that the maximum value of this occurs when x equals 1/2. Right, we can check that the maximum value of this occurs when x equals 1/2. So then when we plug this in, we get that s. So then we get that what? So then r must be equal to, well, if x is 1/2, then negative r must equal 1/4. So r is negative 1/4. And then s equals r plus 2 root negative r. So we can, for plugging in r equals -4 gives s equals 3/4. And then finally, we want to find p squiggle of 1. But since the roots of p squiggle are -1/4 and 3/4, then p squiggle is just equal to x minus 3/4 times x plus 1/4. And then plugging in 1 into this, since we want to find p squiggle of 1, gives something like 5/16 as our answer. So are there any questions about that? Okay, sorry, I went a little over time, but there are a couple of problems that are kind of interesting. So these are, I guess, the homework problems for this week. I think the second one is more interesting, but yeah. So these are the homework problems for this week. So for the first one, we have a and b are polynomials, x squared plus 20x plus c, and we know the value of, we know what a over b plus b over a is. So we want to find root c. Yeah, this one I don't think is very hard. We can just do some algebraic manipulation with thetas. And the second one, we have a polynomial, this cubic polynomial, which has 3 distinct real roots with an arithmetic progression, and each of the roots is 1 less than the root of this. And so it asks what b, this coefficient, is. Yeah, so those are the homework problems for this week. Well, I guess you can do the first one if you want, but the second one is like the actual homework problem for this week, since it's a pretty instructive example. So any questions? No? Okay, all right, thank you.